For this example, we're asked to come up with the shear force bending moment diagram for a beam where the beam is built into the wall there on the left hand side. There's this point load of 10 kips right in the middle. There's a point load of 6 kips upward at C on the right side. Then there's an external bending couple there of 20 kip feet on the right hand side at C. What we want to do is, again, is find the shear force bending moment diagram for that beam. First thing, of course, we need to find a reaction, so that's a very critical first step. So I'm going to use a set of coordinate axes with x to the right and y up. And so for equilibrium, I'm going to be drawing a free body diagram of the entire beam. What we have acting on the beam is our point load, our 10 kips. We have couple in a clockwise sense. There on the right side we have 6 kips up. At the wall we have some shear force, call that VA. We have a bending couple there of MA. And again, our goal here is to find MA and A. Actually, I'm calling it VA. Let me change my name. Let me just treat this, call this the reaction there at A. That would be AY. In order to find these, I'm going to do sum forces in Y. Summing forces in Y have AY, the reaction, minus the point load in the middle plus the point load of 6 there on the end. So from that, I get that the reaction force on the left side, AY, is equal to 4 kips. Easy to see from that equation. Writing down a moment equation, I'm going to sum moments about A. I have the wall bending moment, MA, it's in the negative Z. I have the 10, it's got a moment arm of 6, and since it's in the minus K, I put a minus K there in front. I have the 6 kip force there on the right side. It has a bending moment of the entire length of the beam, so that's 12. It's got a plus sign, and then the couple there on the right side is going to be a minus 20. For equilibrium, that is a 0. From that equation, I get that the bending moment there at the wall is a minus 8 kip foot bending moment. Okay, so that gives us our reactions. Now let's construct our shear force diagram. Let's do that first, and then once we have the shear force diagram, then we can move down to our bending moment diagram there for M. So what I'm going to do is start at the left hand side, x equal to 0. This is x. And I'm going to move myself to the right. So what I have over on the left hand side is that VO is equal to AY. Now AY was a plus 4. By our sign convention on shear force on the left face, positive is up. So that's going to give us a positive 4 kips. If I look at the shear force, they're at the point there of 6 feet, but just to the left of where that point load is applied, I know that's going to be equal to VO plus the area under the P of X curve. Well, between A and B, there is no line load that's applied, so it's going to remain the same all the way across. So that's going to be 4 kips. So as I do this, I'm going to put a 4 here, and all the way across here, I know that it's a constant. All the way just to the left of where that point load is applied. As I move across that point load, I know that it's going to be what it is on the left hand side, and keep in mind that I have a 10 kip force pointing down, so we know that then that we add on our negative 10. Well, the negative 10 is there because keep in mind that our sign convention for external loads is down as a negative. And so any jump that you get is going to be of the same sign as that load. So that's going to give us that minus 10. So in the end, we have minus 6 kips to the right of there. So if I come over here to negative 6, and then say that the shear force then all the way on the right hand side at 12 is going to be what it is at 6 plus. And since there is no line load, there's a zero line load across like that, we end up with a minus 6 kips. Well, that's a really nice result. And the reason I say it's a nice result is that we found that, or we see from the picture here, that there is a 6 kip shear force which is applied on the right side. You know, on the right face, the positive is down. Okay, so since it's pointing up, it's a negative. So the number and the sign agrees with our equilibrium. That's a check. That's always good to have. Okay, so this is a check. Let's do the same thing for bending moment. We're going to start at the left side again and move to the right. So the bending moment diagram is the bending moment at a 0, which we saw here was equal to MA. And keep in mind it's that same sign because on the left face the positive bending moment is in a clockwise sense. So we saw the MA was a clockwise, I'm sorry, we assumed it was clockwise, so it would be a minus 8. This is what we found from above. Now we look at the bending moment there at 6. Well, moving across, we see that it's equal to that plus the integral from 0 to 6 of what the shear force is. So we get the minus 8 from there. The area under the shear force, we could write down an equation and do that, but we just simply have to look at the fact it's the area under that curve. So since it's a plus 4, it's acting over a length there of 6. In the end, what I end up with is 16 kip foot bending moment there at x equal to 6. M12, well, that's M at 6 plus the integral from 6 to 12 of v of x dx. So we saw that M6 was equal to 16. Here the area under the curve, it's going to be a 6 times a base there of 6, but the v of x is a minus, so we need to put the minus sign there. So this ends up giving us a minus 20 kip foot. So on the right face, keep in mind that a positive is in the counterclockwise sense. The negative sign simply means it's clockwise. And on the right side, that's exactly what we found from equilibrium. This agrees with equilibrium. That's a good check. What I mean by this is above, when we found our reactions, we saw that not when we saw for the reaction, the given information is that there's a 20 kip foot bending moment on the right face. It is in the clockwise sense, so it is negative. So just recap what we did. We first found our reactions that allows us to start on the left side and move to the right. Once we found AY and MA, we simply moved from the left to the right using our basic equations. And our basic equations were that V of x then is equal, let's say x2 is equal to V of x1 plus the integral from x1 to x2 p of x. That's how we got all of our equations above there, except we also have that V of x plus is equal to V of x minus plus whatever external shear force that we have got. Our bending moment, we use the equation that m of x2 is equal to m of x1 plus the integral x1 x2 b of x. Now we don't always have to write down the equation for p or v in order to integrate that to find v and m. We can graphically do that integration when they're as simple as that. So I guess I really need to finish up here with my m of x. The plot that I have, again, it starts out here at a -8. We know that m, which is the integral of v is a constant, so it's going to be something with a positive slope. It's going to go up like this. We know that m of 6 here, it was up to 16. And then over there at -20, the bending moment curve is also a straight line, but this case it's got a negative slope because v is a negative. So again, check your work, but use the basic ideas here of integration and the values of shear force at jumps.